Hi everyone, in this video we're going to talk about gases. The general properties of gases was explained to you in 9th grade in states of matter topic. Now in this one we're going to look their properties in detail. But first start with the general properties. Gases have higher amount of energy with respect to its solid and liquid phases. They have no particular shape and volume. They have maximum randomness. The reason of this maximum randomness is that they have maximum distance between its particles. They can be expanded easily and contracted easily. And now comes the most important properties, 4 of them, which are pressure, volume, mole, and temperature. Now what about their units? For pressure, we usually use ATM. We have centimeter mercury, which is 1 ATM is equal to 76 centimeter mercury. Is also equal to 760 millimeter mercury and also equal to 760 torr. We have other units like Pascal and bar, but we don't use them that much. What about volume? Volume, we usually use liters, which is directly equal to decimeter cube. Sometimes the volume is given in centimeter cube, which is directly equal to 1 milliliter. And mole, you have solved some mole problems and we're going to solve it more, combining with the pressure and volume and temperature here. And for temperature, we have 2 important units, which are Celsius and Kelvin. And in most of the questions, not most of the questions, in all of the questions, we're going to take the unit of temperature always in Kelvin, and Kelvin is equal to Celsius plus 273. So let's start with the pressure. Gases apply pressure on the surface they interact. So this pressure can be identified as the applied force per unit area. To measure that pressure, we use 2 apparatus. First one is barometer and second one is manometer. Barometer is used to measure atmospheric pressure, where manometer is used to measure of a gas in a closed container. Now here are some examples for manometers. For example, you have some X gas here and you have P0, which represents the atmospheric pressure. And there is a difference between their mercury levels. The liquid that we're going to use in the manometers is going to be always mercury. Sometimes it can be changed, but in this case, the densities of that liquid and mercury should be given. If there's a difference H here, pressure of X is equal to P0 plus H here. So if there is no height difference between the levels of mercury, you have X gas here, you have P0 here, pressure of X is equal to atmospheric pressure. If that mercury level difference is on the left hand side of the manometer, this means that pressure of atmospheric pressure is higher than pressure of X, and the difference is H. So Px is equal to P0 minus H. Now these are open-end manometers. Now what about if I close these manometers? Let's say that you have closed-end manometers. Let me write the same thing. You have X gas here. You have some mercury level difference here with a value of H. In this case, this part is empty. If this is empty, pressure of X is directly equal to H here. Again you have X here. Again you have a height difference of H here. But in this case you have a Y gas here. Now what about this one? Pressure of X is equal to pressure of Y plus H. What about if the vice versa occurs, meaning the level difference is measured on the left hand side, left arm of the manometer? In this case, let's say that you have a Z gas here. So pressure of X will be smaller than Z. So this is how we do the quantitative calculations for manometers. Let's start directly with the ideal gas law. And the first law for this ideal gas laws, Boyle-Mariotte law, indicating the relation between the pressure and volume. In order to just examine this relation, the other variables like temperature and mole number should be constant. Let's say that each unit is here 1 liter. So this is, let's say that volume 1 is equal to 4 liters. Now this one, volume 2 is equal to 3 liters. This one, volume 3 is equal to 2 liters. So let me say that, I'm just making it up, the first pressure is equal to 3 atm. So what happens when you contract that gas to 3 liters? Does the pressure increase or decrease? Of course, when you contract the gas, the pressure should be increased and it becomes 4 atm. What about the volume is halved? This means that in this case, the pressure is doubled. You're going to end up with 6 atm. Now, will you please multiply all these values, pressure times volume? You're going to find 12 here, find 12 here, and find again 12 here. This means that pressure times volume is always equal to a constant. So when you increase the volume, then pressure should be decreased so that you can have that constant volume. So what kind of ratio do they have? They have indirect ratio. And you can formalize it as pressure 1 times volume 1 is equal to pressure 2 times volume 2. So you can draw the graphic just like this. So next law, Charles law, temperature volume relation. In this case, mole number and pressure should be constant. You're using an ideal piston which keeps the pressure of the container always equal to pressure outside if it's kept at the same place. Ideal piston means it has no friction and its mass is not encountered, meaning not important. Instead of ideal piston, in some of the questions, elastic balloon can also be used. So how does this law work? Now, when you look at the first piston, let's say that again they have equal units. This is 2 liters. So 1 here, 1 here, 1 here, 1 here, 4 liters. So as you see, the volume is doubled. So is the temperature is doubled also. When you look in the unit of Celsius, seems not doubled. But when you change it in the Kelvin, it becomes 273 Kelvin and this is 546 Kelvin. Yes, in this case, the temperature is doubled. So what about graphics? You're going to have 2 types of graphics because you are having 2 types of units in temperature. This is volume, this is temperature, but this is in the unit of Kelvin. Now this one, again volume, this is temperature, again, not again, in the unit of Celsius in this case. So this is 0 Kelvin and here is minus 273 Celsius. So this is known as the absolute 0 point. So you're going to make an extrapolation like this and it will start from, for when you have the Celsius, minus 273, it's going to be like this. So this means that the temperature and the volume, they have direct ratio. Gay-Lussac law, in this case temperature and pressure relation. So volume and mole number should be constant. Now you can guess, in fact, when you increase the temperature, pressure is increased also. So again, they have a direct ratio. But again, please be careful with the units of the graphics. This should be Kelvin and this should be Celsius. You have pressure here, pressure here. It seems to be started from 0. Be careful with the extrapolation. And this will start from minus 273, and it goes like this, same as the volume and temperature relation graphics. And Avogadro's law, this is a law that explains the relation between the mole and volume. At the same conditions, now just be careful here, at the same condition means you have constant pressure and constant temperature. Equal mole number of gas particles occupies equal amount of volume. For example, in the first picture, let's say that you have 3 liters of gas and 3 moles of hydrogen gas, for instance. In the second picture, it seems that you have 2 liters of gas. This means that you have 2 moles of hydrogen gas. This being hydrogen is not necessary. For example, it can be also chlorine. It can be some sulfur dioxide. The type of the gas is not important, but the amount of the gas is important. So when you draw mole versus volume graphic, there is no need for extrapolation, because if there is no gas, meaning no volume, you can directly start your graphic from 0 here. Pressure and mole relation, this is known as the Dalton's law of partial pressure. In this case, volume and temperature must be constant. Now here is the meaning of this law. For example, you have a closed container. You have 2 moles of X gas here and 3 moles of Y gas here. Let's say that this X gas exerts a pressure of 4 atm. So what about 3 mole of Y here? So you can guess there is a direct ratio between the mole number and the pressure. If this is 4 atm, then this should be 6 atm. If the total pressure is asked, you're going to just sum them up and find the total pressure of the container. Now let's just combine all these gas laws that we have taught so far. The real ideal gas law is pressure times volume is equal to mole times R times T here. Now the unit of pressure should always be atm. Volume, liter. The unit of mole is already mole, and temperature always Kelvin. So can you find the unit of R then? When you leave that R alone here, it's going to be atm times liter per mole times Kelvin. So R is the ideal gas constant. So it has a specific value, which is 0.082 or 22.4 over 273. You're going to decide which R value that you should use according to the problem. Or you can write ideal gas law by using the density. For example, instead of volume, you can write mass over density, and instead of mole number, you can write mass over molecular weight times R times T. So yeah, when you simplify these masses, you just left with pressure times molecular weight of that gas is equal to times D times R times T. But just be careful, in this one, the unit of density is not gram per milliliters, but this is gram per liters. Only difference is the unit of density. Now, combined gas law means, for example, when we are explaining the Boyle-Moriet laws, the Charles law, the 2 variables were constant and you were looking at the relation between the rest of it. In this case, for example, mole only constant and pressure is changed, volume is changed, and temperature is changed. So what are you going to do when you just encountered with a question like this? You're going to write PV and RT, and you're going to simplify the ones that are constant. For example, we tell that mole number is constant, R is always constant. So what do you see here? Pressure times volume is proportional to temperature. So you can have that ratio like this. Pressure 1, volume 1 over pressure 2, volume 2 is equal to T1 over T2. So this means that for any kind of gas law question, please do not memorize any formula. Just know PV and RT and derive the needed formula from this ideal gas law. And the kinetic theory. Gas molecules move fast, really fast, and collide with each other. And walls of the container. These collisions are elastic. And the name of the motion that the fluid particles, gas or liquid particles make is called Brownian motion. So what can you say for the kinetic energy of these gas particles, or any particle in fact? The average kinetic energy of different gas molecules are same, this is important, when they are at the same temperature. So as the temperature increases, kinetic energy increases also. So upon this idea, Graham's law of diffusion says, during the collisions, energy transfer occurs between the gas particles, but the average kinetic energy does not change. So what are the results of this does not change term? For example, you have two gases, A gas and B gas. They are at the same temperature. This means that they have equal amount of average kinetic energy. You can just symbolize like this. So what was the formula of kinetic energy in physics? It was 1 over m square. In this case, m times velocity square. In this case, instead of m, we're using the molecular weight, the molar weight of the gases, times velocity of that a square equal to 1 over molar weight of B times velocity of B square. Simplify them. So when you leave those velocities alone here, you're going to see and find a formula like this. So this means that as your gas gets fatter and fatter, it is going to move slower and slower. But this is true for when they are at the same temperature. What can you write instead of this formula? You can write density of B over density of A also. Or you can write the time that effuse through a hole over the time that A gas particles effuse through a hole when they have the same distance. What if they are not at the same temperature? If they are at different temperatures, then formula changes a little bit. Velocity of A over velocity of B is equal to molar weight of B times temperature of A. So the velocity and the temperature has a direct ratio. Molar weight of A times temperature of B. Again, temperatures should be in the unit of course, Kelvin. Now here are the phase diagrams. Now you see two different phase diagrams. The first one is for water and the second one for carbon dioxide. Now what is the difference between two phase diagrams? Now this part is solid. This part represents liquid. This part represents liquid. Now phase diagram means show you the phase of any substance at a specific temperature and pressure. For example, if you have let's say that 200 Celsius like here and under 100 atm pressure, this means that you're going to have that water as liquid form. But when you see this solid to liquid line, this line, you can say that this is the freezing or the melting line. As the atmospheric pressure increases, that line, the freezing point of the water decreases. But when you look for carbon dioxide, Here is that line of carbon dioxide here. This is solid, this is liquid, when this is gas here. When the atmospheric pressure increases, freezing point of that carbon dioxide increases also. So this is an exception for water molecule. Now these points are the critical temperature points. They C here, for example, and B here. When you just get over this critical temperature, apply any amount of pressure, you cannot change that gas into its liquid form. It is called gas then. We're going to just talk about their differences later on. And if we just talk a little bit these graphics, for example, A here, A is known as the triple point. This is a point that you can find this H2O molecule as liquid, as solid, as gas here also. Or let's say that you have C here at constant temperature. When you just increase the pressure like this means that there's going to be a phase change from that part to that part, from gas to solid. So this is a kind of a reverse sublimation, or it is known as also deposition. So by looking at these graphics, you can decide the phase of a substance at any pressure, any temperature. Now the difference between the gas, vapor, critical temperature and pressure. Now vapor is a substance that can be condensed by applying pressure on it at any temperature. When the vapor reaches critical temperature, it is said to be a gas then. And critical temperature is the maximum temperature where a gas can be condensed into liquid by applying pressure onto it. And finally, the critical pressure is the point where the gas cannot be condensed anymore by applying pressure on it. When a gas is at its critical temperature and pressure, then it is said to be it is at critical point. So that combination point that we have shown in the previous slide was the critical point for those substances. Some gases can be used as fluid cooler in the refrigerators and other devices like them. Those gases should have low boiling point and high critical temperature. So that by applying pressure on them, they can turn into liquids by absorbing heat and finally decreasing the temperature of the media. That Freon 12 was the most commonly used coolant fluid, cooler liquid. The difference between its boiling point and critical temperature is very high. And once upon a time, ammonia was used, but it is forbidden because its poisonous chemical effects. And Joule-Thomson effect. James Joule and William Thomson showed that when a gas expands by changing the volume of the container, velocity of the gas particles decreases. So does the energy of the gas particles. Those colder gases also make the surrounding cool. So in fact, this is the working principle of air conditions and refrigerators. And in some questions, you're going to see collecting gas over water. This means that you have, for example, a container here, a closed container, and you have some water in it, and you have some helium gas in it. When we are talking about total pressure in this container, you should not forget about the vapor pressure of water here. So total pressure is equal to pressure of helium, partial pressure of helium plus vapor pressure of water. For example, when you expand that container, like to this one, really big one, again you have some amount of water here and you have helium here. What can you say for their pressures? Now remember, vapor pressure depends only on three factors, which is type of liquid, purity of liquid, and the temperature. If the temperatures are constant in both sides, this means that vapor pressure of water does not change. But for helium, because the volume is increased, then the pressure of helium should be decreased. So you should be careful if you are given a liquid with its equilibrium with its vapor. The vapor of that liquid, vapor pressure of that liquid does not change because the temperature is constant. But helium is different. It has no liquid inside the container, so its pressure is going to be decreased when the volume is increased.